In the last lecture, I explained common emitter configuration of a transistor. In this lecture, we will plot input and output characteristics of common emitter transistor. This is common emitter configuration because emitter is common to the input side and to the output side. We are using NPN transistor in which VBB and VCC are the biasing potentials. I will write this down. VBB and VCC are the biasing potentials. VBB is used to forward bias the emitter base junction and VCC is used to reverse bias the collector base junction. IB is the input current and IC is the output current. The input voltage is VBE and the output voltage is VCE. Generally we have the series resistance here, but for simplicity I have not included the two series resistances in the circuit, and in this scenario VBE is not equal to the forward biasing potential VBB and VCE is also not equal to the reverse biasing potential VCC. So VBE is the input voltage, not VBB, and VCE is the output voltage, not VCC. In input characteristics of common emitter transistor, we need to plot the graphical relation between the input current IB and the input voltage VBE for the different values of output voltage VCE. So we have to plot the relation between the input current IB versus the input voltage VBE, for different values of output voltage VCE. We can also consider the NPN transistor as two diodes connected back to back. So it will look something like this. This is the first diode. This is the second diode. And you can clearly see the input current IB is the current through the second diode and VBE is the voltage across this second diode. This diode is forward biased, so we have the forward bias characteristics of diode as the input characteristics of common emitter transistor. But the important thing is the variation in characteristics due to the output voltage VCE. I will revise this quickly. The input characteristics of common emitter transistor is similar to the forward bias diode because you can see the input current IB is current through the forward bias diode and VBE, the input voltage, is voltage across this forward bias diode. But the important thing is the variation in characteristics because of VCE, the output voltage. I will quickly draw the forward bias characteristics of the PN junction diode. The x-axis is for VBE, this is in volts, and the y-axis is for IB, the input current, this is in milliamps, and you already know how the forward characteristics of the diode looks. Initially the current is 0 when VBE, the forward biasing potential, is very small. Then current starts to increase like this with increase in VBE, and once VBE is greater than the barrier potential, when VBE is greater than the barrier potential, there is exponential rise in the current like this. So this is the forward bias characteristics of PN junction diode. The next thing is the effect on characteristics because of the output voltage VCE. I am considering the silicon diode, so the barrier potential is equal to 0.7 volts. In order to find out effect on characteristics because of the output voltage VCE, we need to revisit the early effect or the base width modulation. We have already discussed base width modulation in the common base presentation. This is emitter region, this is base region, and this is collector region. I am considering NPN transistor in active mode, and in active mode emitter base junction is forward biased and collector base junction is reverse biased. So base is at the lower potential and collector is at higher potential, and the voltage across the collector base junction is equal to VCB, and because of this, width of depletion layer will increase and it will penetrate more in base region because base is lightly doped, and you can clearly see the penetration of depletion layer is more in base region. Let's say width of depletion layer in base region is equal to W and the metallurgical width of base is equal to WB. Width of this region with no penetration of depletion layer is W effective, I am calling this width effective width because recombination of majority charge carriers will take place only in this region. From here we can see W effective is equal to WB minus W, and VCE, the output voltage, is equal to VCB plus VBE. VCE is equal to VCB plus VBE, and if we increase VCE, VCB will also increase. From here you can see on increasing VCE, VCB will also increase. When VCB increases, the width of depletion layer will also increase and there will be more penetration in base region because it is lightly doped, and W will increase. And from here you can see when W increases, W effective will decrease because WB is constant, it is metallurgical width of base, so W effective will decrease. So this is what happens in case of early effect. This is what we call as base width modulation. And now we have to see the effect on input current. When W effective decreases, this means region where recombination takes place decreases, and because of this recombination will decrease. The electrons emitted from emitter will not recombine with the holes in base region, and this will reduce the base current. IB, and the base current IB is the input current, right? So on increasing the output voltage VCE, the base current or the input current decreases. Vice versa is also true. On decreasing the output voltage VCE, the input current IB increases. Now we can easily complete the input characteristics of common emitter transistor. On decreasing the output voltage VCE, the base current or the input current IB increases like this. Let's say this characteristics is for VCE equal to 20 volts, and this characteristics is for VCE equal to 10 volts, and this characteristic is for VCE equal to 1 volt. So on decreasing the output voltage VCE, the input current IB increases. This is in microamps, and this is the final input characteristics of common emitter transistor. The next thing is the output characteristics.